All right, we've done addition, and now we're doing subtraction. And I appreciate you guys kind of sitting with your group people. So we're going to take just a couple of seconds to talk about a few things, and then we're going to turn into our groups and to talk about them among together, okay? So bear with me for just a few minutes while I present some information, and then I'll show you what you're going to do with it. So the first thing is to define what in the world do we mean by subtraction. So when we talk about subtraction, we're saying that that is an A minus B. It's the unique whole number C such that B plus C is equal to A. And this is how we teach kids subtraction initially, is that we talk about sort of filling in the hole or filling in the gap. So when we say things like 5 minus 3 is equal to 2, what we actually talk about to kids is we say, okay, well, what do I have to add to 3 to get 5? Right? What's missing? And that's what's being described here. It's what I'm adding to 3 to get 5. And that is understood as what we mean to be subtraction. Now, there are basically 3 models of subtraction that your book is going to present. There's a 4th one that used to be in a previous edition, and I really hope when they do the editions again, they bring it back, because I think it's a really good one, but it's not there anymore. And so let me show you the 3 that they do show. The first one's called the takeaway model, and this is the one that resonates with a lot of us. I have a feeling that when I was taught subtraction, this might have been the only thing they talked about. Because, and a lot of times when some kids come through, this is the only thing they talk about. In fact, my son, he will tell you, what is subtraction? He's like, it's takeaway. It's takeaway. Like, that would be his definition of what is subtraction. You take it away, something you're taking away. So this is an example of a word problem or description of what we mean with subtraction when we're talking about taking something away. Abby had 24 rocks. Eli sneaked into her room and took 5 of her rocks. How many rocks does Abby have now? So she had something and we removed something from it. This is the takeaway model for subtraction. And we can draw a picture of it if you would like to. So we can definitely think about this in terms of a concrete image. So we're going to have 24 rocks. There's 6 of them. All right, I've got 24 rocks. Eli goes in and he takes away 5 of them. Out they go. And we can count the number we would have left at that point. That's the subtraction here. So 24 minus 5 would give me 19 rocks. Okay? The modeling here is in the language of how we're describing the context. I had something and I'm taking something away. Okay? This is the one that everybody sort of resonates with as being a very strong push for description in your past. There is more than one way to think about subtraction, though, and more than one type of word problem. Missing add-ins is the second one. Lalisa needs to collect 10 leaves for a school project. She and Temeskin go out and find 8 leaves. How many more leaves does Lalisa have? Here, Lalisa doesn't have 10 leaves. She needs 10 leaves, right? What she has is 8. So when we're looking at this, I think that's what it said, right? Yep. She went and found 8. So she needs to have 10. So I'm going to draw 10 leaves. I'm going to draw the 8 that she has. Let me start with that. Here's her 8 leaves that she already has. Okay, it says she and Temeskin go out and they collect 8. So these are the 8 leaves that she has. But she's supposed to have 10, which means we've got some that she still needs to go find, or we could say we've got some that are missing. And in particular, we can draw them in sort of dotted, as though they're not there yet, but they need to be. You can see that the whole picture, when we're done, has 10 in it, right? But within that 10, there's 2 pieces that are sort of drawn in as I still need these. So we still end up with a question that's subtraction. It's still 10 minus 8. It's still the number 2. But it's not because we took anything away, did we? Nobody took away those 2 leaves. She just doesn't have them yet.
We have too little and we need additional.
Right, we need additional. So this one's a missing add-ins model, okay? And then the third one that we're going to look at is called a number line or measurement model. So Akeem drives 15 miles to the mall. And as he's on his way home, his mother calls and asks him where he is. He states he's coming home and he's driven 8 miles so far. How far is Akeem from home? So we did a measurement model when we talked about addition, and we talked about the fact that measurement models always have to do with something that's being measured. Miles is a really good example. We're measuring it, right? We're not actually counting like my leaves or my rocks. We're measuring, all right? It doesn't mean that the problem's any different, but it definitely has the ability to be broken into pieces where other things don't, right? I didn't break the rock in half. I didn't cut the leaves in half. It doesn't make sense. But I can have half a mile, and it does make sense, right? And there's other things. It doesn't have to be miles. We could be measuring things in terms of their height. We could be measuring things in terms of like lengths on, like you guys, was it this class or was my other class where they're measuring like yards of fabric? We can do things for measuring like cooking, you know, like cups and things like that. You can do things from that perspective. There's lots of measurement items you could use, but miles is a pretty good one. So in this model, what we're going to do is we're going to draw a number line. And the number line has Akeem's house right here. And over here, we've got the mall. Right? Here's the mall. That's my mall. And here's his home. And what we know is the distance between them is 15 miles. And we know that he is 8 miles home. So his distance right here is 8 miles. So it is another missing add-end kind of model, right? I'm missing something. He needs to drive a little bit further. I'm missing this length right here. The number that I'm missing, of course, is 15 minus 8. Or 7 miles. I mean, that's what I'm missing. But it's from the perspective of measuring my distance. So I have my 7 miles that I'm missing. Does that make sense? Okay. Here's what you're going to do next. You are going to turn to your group work partners and shift if you need to. I can't remember who you're with. And you're going to write a word problem of these 3 varieties. Okay? You don't have to solve it, nothing like that. I just want you to write a word problem that fits in with this category. Something where you're taking it away, something where you have a missing add-end, and then something where you're measuring something. Okay? So take 2, 3, 4, 5 minutes, something like that, to write 3 word problems. Okay, so this is what we're going to do next. You guys are going to each give me an example of one of the 3 that you did. So I need somebody to volunteer to do takeaway. What's your equation, or what's your word problem that you created for takeaway?
I can volunteer first.
I and then RJ. Okay, go ahead, Ty.
Okay, so Mike has 100 cows. A poacher comes and kills 15 of them.
Wow.
How many cows does Mike have now?
All right, we're killing off the cows. Okay, we had them and then they're gone. RJ, what's yours?
Okay, John has 15 Legos. His sister takes away 5 while he's sleeping. How many Legos does he have left?
Poor John. It was John, right? Bye-bye Legos. Oh, that's so sad. Okay, so somebody took away his Legos. All right, how about missing add-ins? Of my last 4 groups, somebody volunteer for missing add-ins. Miranda.
Olivia needs 16 cookies, but she only made 12.
Oh my goodness, 16 cookies and she only made 12. Those poor 4 children that don't get the cookies, right? So sad. All right, somebody else in missing add-ins. Kiki.
Jennifer has to read 15 pages in her book for her daily reading. She has already read 8 pages. How many does she have left to read?
Oh, that clips close to home when my kids need to read their books, right? 15 pages. She's only read some of them. She has some more left. Yes, that's missing add-ins. All right, we have 2 groups left for number line model. Who wants to go first? Let's start with you, Sydney.
Abby is baking, and she needs milk and eggs, and the chicken coop is 5 miles away, and the cows are 7 miles away. How many miles does she need to walk after she gets the eggs for the milk?
Excellent. So she's got to go walking to find her locations for her milk and her eggs. Right, cool. All right, and then our last one. What you guys have?
Scotty drives 16 miles to Sphere at Halloween. On his way home, his wife calls to ask where he is. He says he's driven 6 miles so far. How far is Scotty?
All right, so Scotty's driving and he's coming back home and we need to figure out how much he has left to go. Very good. All right, so here's the point, is that in real life, subtraction problems do not show up and say 5 minus 7 or 7 minus 6 or whatever. They don't say these are the numbers and subtract them. You have to infer them from the context of what's going on, correct? And there's more than one context that's going to say, hey, I need to subtract. So what this does for you as a teacher, besides just aid in your teaching, is that if you see that a child can consistently do take away just fine, but every problem they miss is a missing add-ins problem, then you understand that the problem is not, I don't know how to subtract. The problem is that I don't understand the structure of this language. Does that make sense? That's what's going on here. Okay, so what we're going to do next is we're going to talk about some properties of subtraction. Whole number subtraction properties. And we're going to take the same 4 properties we had for addition, and we're going to explore whether or not they hold for subtraction. So the first one is closure. It was probably nobody's favorite property. It's kind of a struggling one for all of us when we get to these other number systems. But closure was the idea with addition that when we added 2 whole numbers together, we get another whole number. The question is, does that work for subtraction? If I subtract 2 whole numbers, do I always get a whole number? The answer is no, actually. But if you say no, you got to be able to tell me why not.
Because negative numbers are not whole numbers.
Okay, so Ty, can you give me an example of how that works?
2 minus 8.
All right. 2 and 8 are whole numbers, but when I subtract 2 minus 8, I get negative 6. And this is not a whole number, right? So subtraction doesn't hold. Closure doesn't hold for subtraction. How about commutative? Commutative is the idea that the order in which we added our numbers together didn't matter. 5 plus 2 is 2 plus 5. Does this hold for subtraction? Sydney says no. How come, Sydney?
Because 8 minus 6 does not equal the same thing as 6 minus 8.
You're right. 8 minus 6 and 6 minus 8 don't equal one another. So we're 0 for 2 right now. 2 properties, neither of them hold. No closure, no commutativity. Associativity is a little bit harder to justify, so I'm going to do this one for you. We just want to see, it's going to be a no. Let me just tell you that right now. We want to see if the subtraction order and grouping matters. So we're going to do 3 minus 2 minus 1. And then I'm going to do 3 minus and 2 minus 1. Whoa. There we go. All right, so if I do this first half, what is 3 minus 2? 1. And then what's 1 minus 1? 0. So this direction is 0. Over on this one, what is 2 minus 1? 1. And then I have 3 at the beginning minus that 1, and I get 2. So associativity doesn't work either. And in fact, it can work worse than this. When I created this on purpose to keep getting whole numbers. But you could definitely create a problem where you already end up with a negative in the middle of all of it, right? The subtraction order actually just pushed us into the negative zone. And then the last one's identity. So with addition, we had the identity property that said if I add the number 0 to another number, like 5, 5 plus 0 and 0 plus 5 both equal 5. Do I have an identity for subtraction? Be careful. The answer is no. Ty already told us one, though. Does somebody else want to tell me why this one's a no? Or give me an example? Okay, Ty, you get it back then. Can you tell me why?
Well, 7 minus 0 is not the same as 0 minus 7.
Yeah. So 7 minus 0 is, in fact, 7, which is probably what everybody who said yes was kind of thinking. The problem is it has to work in both directions, and 0 minus 7 does not equal 7. So the identity has to work both directions. It has to be commutative, and because commutative doesn't work already, the identity is not going to work either. Does that make sense? Kind of because one is failing, it's forcing the other one to fail. So the long and short of it is that none of our properties work for subtraction. None of them. Okay? We'll explore the same questions when we get to multiplication and division as well. What holds, what doesn't hold in each of those cases. So what we're doing next then is looking at algorithms for subtraction. So these are ways to subtract. That's what the word algorithm means, right? Like the algorithm, computer algorithms, right? It's the way in which your computer is doing something. These are algorithms for subtraction. And many of them, not all, but many of them are going to have sort of a counterpart in what we already did with addition. This first one's an example. It's the concrete model. So the concrete model looks like the base 10 blocks. Okay, so when you see and hear the word concrete, it's talking about those blocks. So when it says 34, it means I have 3 longs and then I have 4 units. and I want to subtract, I want to remove, I want to take away 18 of them. Well, 18 is one long. That's no problem. I can take away a long from here, right? There's lots of longs to take from, not a problem. But I need to take away 8 units, and I don't have 8 units. I only have 4 units. Okay? So if you were doing this in a classroom with children and you were using this, this would be, like a single standalone lesson kind of thing that you probably do several times in class as the kids work with it. You'd have physical objects. And what you would do is you'd physically take that long and you'd break it apart. Right? Think Legos that are stuck together kind of thing. You would physically break one of these longs apart. So my picture, instead of looking like what it does right now, would change as follows. I would take one of these and I would replace it with 10 longs. They're all broken apart. So these are actually equal, right, from here to here. And then looking at this diagram, can I take a long away? Sure. And can I take away 8 units? Sure. Just need to figure out which ones are 8. So there's 5, 6, 7, 8. I think that's 8 of them. That looks right. So I'm going to take away all these objects that I've sort of marked here. And why? Well, because it says I'm going to subtract 18, right? It says to remove 18. And what's going to remain when I'm done is going to be 1 long and how many units? 6. And so my solution is that I have 16. So this is concrete model. This is where you would start in a classroom with the young ones and the idea of subtraction and physically doing this. What we tend to get to as an end result is wanting to do what's called the standard algorithm. So let me show you what the standard algorithm looks like. You know this one, but we'll remind you. So the standard algorithm means we start in the ones column. And we attempt anyway to say, in this case, 4 on the top minus 8, and I subtract. The problem is I can't take 8 away from 4. There's not enough. And so I have to regroup or borrow. I need to take the number 3 and turn it into a 2. And then I need to add that 10 into the 4. So sometimes people will write it like that. Sometimes people will mark it out and put the 14 right here. That doesn't run, either of those are fine, doesn't matter. But I'm borrowing or I'm regrouping one of my 10s to make 10 ones. Now I have 14 minus 8. So what's 14 minus 8? 6. And then 2 minus 1 would be my 1. Okay? I'm regrouping, I'm borrowing, those sorts of things. With small enough numbers, this is not a big deal. It's fine. The kinds of things that end up happening with children is when they have to borrow after borrowing after borrowing. Just like you saw us happen in section 3.1, when there's a bunch of zeros there and you have to keep moving things over and then shifting them, is that sometimes we lose a number in the process, those kinds of things. But this is a standard algorithm. Kind of a bridging between these two is called the expanded algorithm. So these 3 so far have all been things we've seen before. So we take the 34 and we write it as 30 plus 4. And we take our 18, write them as 10 plus 8. Okay, so we're breaking it apart into its components by place value. And I'm supposed to be subtracting, which means I'm going to do a minus here and a minus here. Well, that's fine. I can do 30 minus 10, right? Working from left to right. But again, I'm at the point where I can't do 4 minus 8. So I have to regroup. But here you can actually see what's happening. I'm taking the number 30 and I'm taking 10 away. It's now 20. And I move that 10 over with the 4 and I make it 14. Like you can see the shift, right? The number didn't go anywhere. It just changed its locations, to the other spot in the line we're on. And then I subtract again. 14 minus 8 is 6. 20 minus 10 is 10. And I have 16 when I'm done. So especially for a child who's seeming to understand what they're doing with concrete model but struggling to get to the standard algorithm, this is a really good in-between one to justify what's happening as you're shifting those numbers around. All right, the last algorithm for subtraction is equal additions. And while we don't have an equal additions algorithm for addition, we do have something that's very similar. It was called opposite change or trading off. So the idea is that we don't want to borrow. Okay, that's the goal. So, whoops, that was an 8, wasn't it? So there's a couple things. This is going to be a no borrow zone. No borrowing. And the way that we're going to get it still is because we want to get lots of zeros. But we want to get lots of zeros in the second number. That's the number we're subtracting away. So our goal when we did opposite change was to get lots of zeros so that we didn't have to regroup. I mean, that part's the same, but it didn't matter whether the zeros were on top or on bottom. Here, it matters when the zero's on bottom. So I take the second number, and I always affect change to the second number. So if I'm taking 158, and I do it place value at a time, how would I make the 8 into a 0? We would add 2. So we're going to add 2 here. But when I do this, I add equally. It is equal additions. I will add 2 to the top as well. With opposite change, whatever I did, I affected it by doing the opposite. Right? Because this is subtraction, I'm doing it the same. So this becomes 836, and this one becomes 160. Now, if at this point I could subtract without borrowing, that'd be okay, and I could do it. But I can't. I'm good in the ones column, 6 minus 0, but I'm not good in the tens column, 3 minus 6, right? So I need my 6 down here to be a 0. What do I have to add to 6? Think just single 6 now. What would I have to add to the number 6 to get a 0?
4.
I'd need 4. But this is in the tens place, so instead of adding 6, I'm going to add 40. Instead of adding 4, I'm going to add 40. Yes, you guys got it. I just wasn't saying it right. So we're going to add 40. Top and bottom. All right, so this one becomes 876. What does 160 plus 40 become?
200.
That's 200. Now, can I subtract without borrowing? Yes. Now I'm good to go. If I subtract, what do I get?
676.
676. Okay, equal additions.
So you add for both,
Mm-hmm.
like the other one, you added one, subtracted one.
Yes, so you're compensating because it's addition. You're adding 2 pieces together. So if I'm adding 2 pieces together, whatever their weights are, and I add a little bit to, we'll do it this way, we'll do like scale. I'm adding a little bit to one, I need to subtract a little bit to the other. That way, once again, I haven't actually changed the value overall. When I take the 2 numbers that are being subtracted, if I want to find their difference, if I subtract one, I'd have to subtract the other one to keep the difference between them the same. Or if I add one, I'm going to have to add a little bit to the other one to get the distance again between them to be the same. Yeah. Okay. Let's take a look at other bases. So let's do a little bit of subtraction in other bases. I know it's our favorite, so we definitely should do it again, right? Yeah, of course. Right. All right, so we're looking again at base 8. Our numbers are 3, 4, base 8, and 1, 7, base 8. And I want to work with you both the standard algorithm and one more on each of the problems like we did last time. So if I have 3, 4 minus 1, 7, and I'm working in the standard algorithm, then I'm regrouping. The regrouping means the 3 becomes a 2. But this is base 8. Okay, so in base 10, when I regroup, from the tens column, I add 10 to the ones column, right? But this isn't the tens column anymore, it's the eights column, because I'm working in base 8. So when I borrow in base 8, I borrow 8. So this 4 has an 8 added to it, which gives me 12. I don't have 14. I have 12 because I only borrowed 8. If you think of it in terms of the physical Lego kind of pieces, right, what we physically did is we took a long, but the long's only 8 long. So when we broke it into pieces, I still only have 8 little units left to combine with the other units that I have. So we're going to have then 12 minus 7. So what's 12 minus 7? 5. Yeah?
Why can't we do 12 if it's only up to?
We're just it's the same. Let me actually go back here and answer that from here. The same question could be applied, Savannah, to why do we have a 14 written in a single digits column?
Oh.
Right? It's a part of the regrouping process that allows us to take some things away. So that's what's going on. Yeah. And 2 minus 1? 1. So this is the number 1, 5. Remember your base 8 next to it.
Okay, wait, I have another question about that.
Okay.
So I get like if you change a number, but now that I'm thinking about it, like why wouldn't it be like stop at 8 and then go 1, 0, 1?
it would. That's why it's in the other column, actually, is because that 1 got pushed over into that column. But that 1 that we're borrowing was representative of 8 units. So anything in this column of longs has 8 that make them up. They're 8 long. Let's see which one I have written down. I thought so. Let's try opposite change, and it might make it a little bit easier to see what's happening. Not opposite change, I'm sorry. Equal additions is what I meant to say. So we have to subtract with borrowing if I keep the numbers the way they are. So what I want is this 7 not to be a 7. I want it to be a 0. In base 8, how many have to be added to the 7 to make the 7 become a 0? Just 1. Okay, so if I add 1 here and I add 1 here, goodness, the 3, 4, becomes a 3, 5. What will the 1, 7 become? 2, 0. The number after 1, 7 is 2, 0. And then what's 3, 5 minus 2, 0? 1, 5. Base 8. Let's do one more. So we're doing a 3-digit number. We'll do standard algorithm first. And then I think I'm going to do expanded on this one. So the ones column is very friendly. I've got 2 minus 0. So when you have the opportunity, don't go making things hard. Just do it, right? This is 2. It's all good. The 3's column, which is our next one over, though, is not so friendly because it's 0 minus 1, right? So I'm going to have to regroup, and I'm going to have to borrow for this one. But if I move 1 column over, which is the 3 squareds column, I don't have anything there to borrow from either. So I have to move 1 more column over, right? And this 1 will get borrowed from. But when I borrow 1 in base 3, how many am I borrowing? 3. I'm borrowing 3. So whatever base you're in tells you the amount that you borrow. All of my longs are 3 long, right? And this one would be, this one where I just did it would be a block. So I take a block and I take away one of the flats that makes it a block, and then I turn it into longs, and then all the pieces get broken apart, okay? So my block previously was 27. And if I break it into flats, there's 3 flats that piece together to make my block. So now I have 3 flats. But I want to borrow from the 3 flats to make it 2 flats. And now I take a flat, which is a 9 by 9, I break it apart. And when I break it apart, it makes 3 longs. So I have 3 longs. So previously a block, broken up into 3 flats, and then one of those flats breaks up into 3 longs. We're always borrowing 3 in base 3. Then I can do it. 3 minus 1 is 2. And then 2 minus 1 is 1. So this is 1, 2, 2, base 3. So let's show what this looks like. I don't have this done in an expanded form. We're going to do it that way anyway because I want to try. Okay, so I have 1 in the 3 squareds column. I have 0 in the 3 to the first. Did I get that right? 3 cubed is what I meant to put there first. 3 cubed to the first one, 3 squared on the second one. 3 squareds column. I have 0 in the 3 to the 1 column, and then I have my 2 in the units. Okay, that's what this is in expanded form. These are the powers of 3. And then I'm going to subtract off a 1 in the 3 squareds and a 1 in the 3's place and a 0 in the 1's place. So the 2 minus 0, all these are subtracted, by the way. The 2 minus 0 is, of course, 2. I can't borrow. I've got to come all the way over here. So if I break my 1 apart, or if I take my 0 and I break my 1 apart, I now have 3 flats. Right? I have three objects of size 3 squared. Those are flats. And then I take from one of those. I take one of those away, I should say. And I break the flat into 3 longs. So 3 longs. So 3 longs minus 1 long is 2 longs. And then 2 flats minus 1 flat would be 1 flat. And I have the number 1, 2, 2, base 3. Okay, here's what we're going to do. The last 3 questions are very quick. I can finish them in the 2 minutes we have, okay? But we will table all of the work to be completed. We'll do group work on Friday, and this will be due on Monday. Cool? Okay, let me finish my 3 questions. This is all mental math, which means math done in our heads, and it also means that you still have to show it because I can't see inside your head. Everybody remember that from the first section we did this with? Okay. The first one, called breaking up and bridging, works as follows. We break up the second value into its place values, 30 and 8. I take the first number given, 46, and I take off the tens place, 30. 46 minus 30 is 16. And then I remove the ones place, which here was 8. And 16 minus 8 is 8. 3 steps, right? Break it up. Subtract these, and then I need to find my final answer. All right. Ooh, we got a phone. All right, cool. Trading off. Trading off means the same thing as equal additions. So equal addition here. So we have 46 minus 38. I'm trying to get us to not borrow. So we add 2 here, which means we add 2 here. This gives me 48. This gives me 40, and if I subtract, I have 8. Okay? And then the last one is dropping the zeros, which there's another name for this. Somebody mentioned it the other day, and when they said it, I was like, I need to remember that when I teach this, and I've already forgotten what the name was that they had seen it used as. But when we have those trailing zeros, the idea is that because there's the same number here in both of them, is we can ignore them. And we can focus on the fact that this is really just the same as 46 minus 34. Right? You probably do this automatically when somebody says something like 50 minus 40. You don't think 50 minus 40. You think 5 minus 4, probably, and use that fact. Same thing here. So if I did 46 minus 34, I'd have 12. And then I have to tack on the part that I was ignoring at the end, my zeros. So this is 1,200. Tailgate. Was it you and I that were talking about? There you go. She called it tailgate. Thank you, Lainey. I couldn't even remember who I was talking to. Man. All right, tailgate. Cool. So we're going to stop there for today. Homework will not be due next time. If you'd like to start it, you certainly may. But please don't do the group work. We'll do that in class. Okay?